Hello again, welcome to the third of the revision videos on the normal distribution. This time we're going to look at finding the parameters mu and sigma using standardized normal distribution. So a standard normal distribution, as we call it, is a normal distribution that has set parameters. We call it the Z distribution. It is a normal distribution, but this time the mean is 0 and the standard deviation is 1. All right, and this distribution looks just like any other distribution. We've got 0 here, and using our facts about the normal distribution, we know that if we were to draw in a standard deviation, so the standard deviation is 1, 1 above 0 is 1, 1 below 0, minus 1. The area in between those two, as we saw in the first video, is approximately 0.68. So that's our standard normal distribution and some facts that we know about it. The 0.68 isn't massively important to this at this point. Now, why do we need to use it? Well, if we don't know either mu or sigma or both, then we can't use the calculator because we've got nothing to type in. So we need this because we have a mu and a sigma that we can use. Now there's this little conversion formula that at some point you have used and you've no doubt learned. It is something you need to memorize. It's not given to you in the formula book. It looks like it is, but the one that's in the formula book is linked to hypothesis testing and is different, subtly different. So let's have a look and see where this little formula comes from. I'm going to invent a distribution and I'm just going to call it a normal distribution with a mean of 7 and a standard deviation of 2. Okay. So there's my normal distribution, mean of 7, standard deviation of 2. Now, if I draw in these little key values again, where my area in the middle is 0.68, right? We know that this value over here is going to be 1 standard deviation above the mean, which for this is 7 plus 2, which is 9, and 1 standard deviation below the mean is down here, which is going to be 5. So these two graphs can be used in conjunction with one another. But where does this little formula come from? Why does it work? The reason it works is basically it linked to the transformation of a graph. Okay. How do we get from the current mean to the mean that we need for the standard normal distribution, i.e. the Z value? Well, we subtract it. We do 7 minus 7, which is 0. So by subtracting the mean, we turn this 7 into 0, which is why we subtract the mean. And then to get a standard deviation of 2 down to a standard deviation of 1, we can't just use subtraction because that would have the effect of moving the whole thing to the left. So rather than use subtraction, we use division, which shrinks the standard deviation closer to the mean. So if we've got a standard deviation of 2 and we want to get it down to 1, we divide by 2, which is why the standard deviation is always divided. Okay? Divide the standard deviation by itself, you shrink it down to a standard deviation of 1. So that's where this little formula comes from. How do we use it? So we've got this question over on the right here. The random variable x distributed normally with a mean of mu and a standard deviation of 3. So I'm just going to quickly sketch that in. Mu, we don't know. What we do know is that the probability of x being greater than 20 is 0.2. So I can add that into my diagram. Oops. Good for these straight lines, am I? So there we go. So I know that to the right of 20, when I shade the area like this, that's 0.2. So that's all that I know about this distribution. So I'm going to draw the same distribution, or another distribution. This time, it's going to have the mean of 0. So this is our x distribution. This is our z distribution. And what I'm looking to do is to find a z value that gives me exactly the same area to the right, 0.2. Okay. And once I've got that z value, I'm going to substitute into this conversion formula, and hey presto, I'm going to have my mean. So let's use the inverse normal. Okay, so we've got the probability that z is greater than little z is 0.2, so we can work backwards using inverse normal. When we do that, we find, so area 0.8. If you're using the class words, you need to do 1 minus 0.2. Remember, it only works to the left. If you're using CG50, select the right tail. And so our value here is 0.8416. Now that's the z value that directly corresponds to the 20. Okay? They have the same proportions. So I'm going to use this conversion formula, z equals x minus mu over sigma. And I'm going to substitute the information that I know. So z is 0.8416. Remember, this is the z value from the z distribution. X is the 20. That's the value that the 0.8416 maps to. Mu is our unknown, and sigma is 3. And if we solve this little equation, we just end up with, so times by 3, add mu, take away, so we'll have 20 minus 3 lots of 0.8416. And so our mu will come out as, there we go, some fast calculator work, 17.48 to 2 decimal places. And that makes sense, okay, because the mean we were expecting to be less than the 20, and that's exactly what happens. So that's how we use the standard normal distribution, and in fact that's why we use it, right? Because we don't have enough information. If we don't know mu or sigma or both, we don't have enough information to substitute values into a calculator. All right, here goes. So this is the last question for this video. This time we've got both parameters missing. So our x distribution here is just a little bit, not useless, but not helping. So I'm going to draw it anyway and have a look at what it looks like. And we're going to combine it with the information that's given in the question. So here is my normal distribution. That is mu. Now I'm told that greater than 35 is 0.025. So the 35 is going to go over there. So there's my 35. My area to the right of that is this 0.025. Okay, so that's this marked in. I'm also told that less than 15 is 0.1469. So my 15 is going to go on this side. And I'll shade that in green as well. So less than 15 comes out as 0.1469. So here is the situation, right? We've got a lot of information going on here, but what we don't have are the two vital pieces that will allow us to do any work on a calculator. So I'm going to go over here and I'm going to draw my z distribution, 0, 1 squared. And the z distribution, remember, is standard bell curve shape, but the mean is 0, standard deviation is 1. I'll just quickly draw that in. There's my 0. I'm also going to replicate the probabilities that I drew in my original sketch. And doing that, so the probability over here to the left, 0.1469, the probability over here to the right, 0.025. I'm going to call this Z1, and I'm going to call this Z2. Doesn't really matter which way around it is. But we can actually work out what Z1 and Z2 are using the inverse normal calculation. So let's do that. The probability of Z being greater than Z1 is 0.025. That's from this side here. So Z1, if we use the inverse normal, it's going to come out as 7, inverse normal. The area is going to be 1 minus the 0.025. So 0.975. And all the rest of the parameters are the same. So Z1 is going to be 1.9599 Yeah, 1.96. Oh, let's leave it to 4 dp. Okay. We also know that the probability that z is less than z2 over here is 0.1469, and so z2 using the inverse normal comes out as minus 1.04 or 0.50. Okay, so that's our z1 and our z2. z2 is negative because it's below 0. So all we do now is substitute in. We've got our conversion formula. Z is x minus mu over sigma. And so for Z1, I've got 1.960 equals 35. Remember, the Z1 maps to the 35. Minus mu divided by sigma. And then for my other Z value, I've got minus 1.050 is equal to, so Z2 maps with the 15. And we've got 15 minus mu over sigma. So we've got two unknowns in each equation. We're going to have to solve these simultaneously. So one thing we can do is we can make them both equal to mu. So mu is going to be this times this. So we've got 35 minus 1.960 mu. Sorry, sigma. And for this equation, we're going to have mu equals 15 plus 1.050 sigma. And it's plus because we're subtracting the negative. And we can make those two equal to one another and work out what sigma is. So let's do that. I'm going to have 20 equals, calculator in the right mode again. So 3.41 sigma. So the standard deviation is going to be 20 divided by this, which is 6.64. 2 decimal places. And when we know that sigma is 6.64, we can substitute this back in. So we'll say we're going to sub it back into this first equation. 1.960 equals 35 minus mu divided by 6.64. Okay, so should be equals. So that means that mu is going to be 35 minus 1.960 multiplied by the 6.64. 35 minus 1.60 times answer, which comes out as 21.97, so 21.98. And we have done. We have calculated sigma, 6.64, and mu, 21.98. Now that's it. There's nothing else to that. It does take a bit of practice, and there is a lot of work involved. But map your real life distribution to the standard normal distribution, find your Z values, use the conversion formula, and solve simultaneous equations if you're trying to find both, or just solve the single equation if you're trying to find one of them. Okay, next video we'll be approximating a binomial distribution using a normal distribution. Thanks.